Okay, good morning, everyone. Let's get started. So this morning session, we have two speakers. The first speaker, Dr. Huang Qing-Guo from Institute of Theoretical Physics, Chinese Academy of Science. Professor Huang, his major research area include physics in early universe, dark energy, and some conceptual problems of quantum gravity. And recently he got interested in gravitational wave. And today he's going to tell us about so the title of the talk is Search for Gravitational Wave Background in Pulsar Timing Array. So please, thank you.
Okay, thank you for your introduction. So today I'm very happy to be here to introduce our recent result about search for a gravitational wave background in pulsar timing array. We know in nature there are four fundamental interactions. The weakest one is gravitation. And now we know the gravity is governed by the general relativity. The matter tells us how the space-time is curved, and the space-time tells the matter how to move. So in general relativity, there is a very famous prediction is there should be a black hole in our universe. This is quite different from Newtonian gravity theory. There should not be a black hole. So once we observe black hole in our universe, we can prove general relativity should be correct. Besides, there's another solution for general relativity. It's called the gravitational wave. Once we do a small perturbation around Minkowski background, and we find this perturbation satisfies a wave equation. And this wave is real and can carry energy. This is a very important point for the gravitational wave. That's why we observe the size of orbit of this binary shrinks due to the gravitational wave carrying out the energy from this binary system. This provides the indirect evidence to say there should be a gravitational wave in our universe. Of course, we still expect to see the gravitational wave change the space-time of our universe. We know the gravitational wave in general relativity is transverse mode. So here we consider a gravitational wave propagate around this direction. And there are two perpendicular directions. One is x direction, another one is y direction. Because general relativity predicts the gravitational wave should be a quadruple radiation. So the gravitational wave can stretch space along direction and will press this direction. So once we observe this effect, we can say we observe gravitational wave. So fortunately, after the prediction of general relativity 100 years later, we directly observe the gravitational wave radiate from these black hole binaries far away from Earth. And this gravitational wave carry a very huge energy from this binary system. Of course, this detection won the Nobel Prize in 2017. So now we know there are a lot of galaxies in our universe. This is our Milky Way galaxy. And we know in the center of Milky Way galaxy, there's a supermassive black hole with mass around 1 million solar mass. On the other hand, because there's a strong gravity between different galaxies, and the galaxy will collide with each other. And this collision is not so real. And for example, our Milky Way start to collide with the Andromeda galaxy. And sooner or later, these two galaxies will merge with each other. And once two galaxies merge, we know in both of them there are supermassive black holes in the center, and these two supermassive objects will sink to the center of the new galaxy and form a supermassive black hole binary. Once they move around each other, this binary will generate a gravitational wave, a very long wavelength or low frequency gravitational wave. This gravitational wave can propagate to our galaxy and change the distance between the pulsar to the Earth. And then we can measure this pulse from pulsar to detect such kind of low frequency gravitational wave generated by the supermassive black hole binaries far away from Earth. This is the basic idea for us to detecting low frequency gravitational wave by using pulsar timing array. So now we know there should be many supermassive black hole binaries. All of them can emit gravitational wave. And finally, all of these gravitational wave will form a stochastic gravitational wave background in our universe. And we can use the pulsars in our galaxy to detect such kind of gravitational wave background. This is what we want to explore today. So how we can say we detect such kind of background or not? First of all, we should see some stochastic signal with roughly have a power law energy spectrum. Because these two black holes move around each other, because gravitational wave carry out some energy from this binary, and the frequency of this system will grow up and finally form such kind of power law energy spectrum for the supermassive black hole binaries. So we should see such kind of stochastic signal first. And then we need some criteria to say whether this stochastic signal is gravitational wave or from other signals. So we need to calculate the signal from different puzzles. There should be some correlation between the pulse time of timing. They will have a different time of arrive, and we can measure the correlation between this between the TOA from different pulsars. Around 40 years ago, Helen Dance predict gravitational wave should tell us a special correlation between the different TOA. So today we call it a Helen-Dance curve. Previously, we already told you that because gravitational wave in general is quadrupolar radiation, and from the one direction, if the space is stretched, another one will be pressed. And roughly speaking, the angle 0 and 90 degrees should have an opposite sign here. This is the characteristic feature for gravitational wave. Once we prove or measure such kind of correlation curve, we can say this stochastic signal is from has origin of gravitational wave. So in last year, several pulsar timing array collaboration claim they detect such kind of correlation. It's mainly from the NANOGrav, EPTA, PPTA, and the Chinese Pulsar Timing Array. Let's see what they observed in last year. So here we show the spectrum from different PTA collaborations. It's clearly the NANOGrav, EPTA, and the PPTA give us a roughly power law spectrum here. But unfortunately, because the Chinese PTA only run around 4 years, so they cannot precisely measure such kind of spectrum, and we can see the question on the feature of spectrum is quite poor. We hope in the near future, CPTA can significantly improve their results. So another key point is that whether they really measure the head distance curve or not. So here we show their results. This is NANOGrav, EPTA, PPTA, and the CPTA. So overall, we see that the error bar is quite big, right? It's quite big. So maybe we still cannot definitely to say that they already measure such kind of head distance curve, including the Chinese PTA. So let's see what they claim in their paper. First of all, let's see the abstract from NANOGrav. They just report a multiple line of evidence for stochastic signal. Let's correlate it among the 67 pulsars from the 15 years pulsar timing dataset. And they also claim that the correlation follow the head distance pattern expected for a stochastic gravitational wave background. But we see that their p-value is not small enough to claim detection. So they only have around 3.5 to 4 sigma evidence to say this signal may be the gravitational background. So finally, they also claim that the observation of head distance correlation points to the gravitational wave origin of this signal. So anyway, they didn't claim they already detect such kind of gravitational wave background in their data set. And another thing I want to point out is that, so before the 15 years data release, they also released 12.5 years data. And they only have 2.5 years more data, but the best factor is improved from the 4.5 to 200, around 200, right? And but the shape of spectrum is quite different. For example, the spectrum index is gamma. In the 12.5 years data is larger than around 5. But 15 years data give us a much smaller index, gamma, around 3. So we see that they only add 2.5 data, but many things geometrically happened, right? So now we still do not we do not make sure their data set is reliable or not. We observe that only have 2.5 more years data, many things geometrically changed. And let's see what the EPTA claim. They do some interesting data analysis. Totally, they have around 25 millisecond pulsars. And the full observation is 24.7 years. But they separate the full data into two parts. One is the full 24.7 years data, and they also have 10.3 new observation data. They didn't find anything in the full data set. They didn't find any signal about the gravitational wave in the full 24.7 years data, but they claim that the latest, the new 10.3 years data from this is from new generation observing system shows non-negligible evidence for gravitational wave background, but they didn't see any evidence for the gravitational wave background in their full data set. The PPTA, they also do another interesting check, and they find that they demonstrate that the apparent signal strength is time dependent. And the first half of their data set can be used to place an upper limit on the amplitude of this stochastic signal. But this upper limit is in tension with the inferred common spectrum amplitude using the complete data set. So they think maybe this signal strength is time dependent. So anyway, so they just have a very weak false-alarm probability for such signal to be a gravitational wave around 2 sigma. This is the Parkes Pulsar Timing Array dataset results. So this is the Chinese Pulsar Timing Array dataset. They claim that once they search for the head-distance correlation curve, and they find some evidence for this head-distance correlation has a 4.6 sigma statistic signal, but just only for one discrete frequency around 14 nanohertz. They didn't see such kind of correlation in other frequency band. So they also expect the future international Pulsar Timing Array dataset, data analysis, and the next Chinese Pulsar Timing Array dataset will be more sensitive to the nanohertz gravitational wave background. So anyway, now after they release their data, International Pulsar Timing Array also do some further analysis to check whether these different collaboration results are consistent with each other or not. So they only give us the analysis for the EPTA, PPTA, and the NANOGrav. The reason is that only these three collaborations release their data. So as I know, the Chinese Pulsar Timing Array collaboration has not released their data up to now. So here we see that this is the strength of the signal. This is dashed line. And this three curve is the sensitivity curve for these three different Pulsar Timing Array. So we see that the PPTA has worst sensitivity. So that's why the PPTA cannot give some evidence for this gravitational wave background signal. But the NANOGrav and the EPTA has a much better sensitivity and in the low frequency region, and we see that the sensitivity of NANOGrav and the EPTA is lower than the signal. That's why they can see some evidence for the gravitational wave background in their dataset. For me, so if this signal is really come from the gravitational background, I think the most promising gravitational wave source should be the supermassive black hole binaries. Because we already observe a large number of gravities, a large number of galaxies in our universe. And we also observe the collision of galaxies. And once these two galaxies merge, and finally we form a supermassive black hole binary and can be detected by the Pulsar Timing Array. So here we use a 18-parameter model to try to explain what they observed. This model is proposed by Siyuan, Cesana, and Consolis. In their model, there are 18 parameters. Fortunately, some of these parameters has been constrained by astrophysical observations. But there are still some free parameters for us. So we propose to use this new dataset, the gravitational wave dataset, to constrain the following, please. Galaxy mass function, yes. Yeah. So only one thing I want to stress that we try to concern the initial eccentricity of a supermassive black hole binary. And if we find the dataset prefer a large initial eccentricity, so which implies that maybe in the future, we try to search for some individual supermassive black hole binaries. We should take the eccentricity into account. Once we take eccentricity into account, the waveform is quite different. So at least for the Pulsar Timing Array search, we should take this eccentricity into account. And once we fix these parameters from the NANOGrav, and we can predict the merger rate of supermassive black hole binaries. And we see that the merger rate of the supermassive black hole binaries with triple mass from the 10 to 5 to 10 to 7 solar mass. And the redshift is from 0 to 5, is estimated as 0.5 per year. And we also extrapolate the low frequency gravitational wave background to the high frequency. Because in this mass region, they can generate high frequency gravitational waves. And we see that maybe in the future for the spaceborne gravitational wave detector like LISA, Taiji, and Tianqing, we will have opportunity to detect such kind of strong gravitational wave background in the spaceborne gravitational wave detectors. So finally, let me give you a brief conclusion and a discussion. So recently, NANOGrav, EPTA, PPTA, and CPTA independently report a strong evidence for a stochastic signal consistent with gravitational wave background. Although we do not have substantial evidence, we may be beginning to detect the gravitational wave background. And the supermassive black hole binary provides one of the most promising gravitational wave source for the stochastic signal detected by PTA. But we still have more opportunity. We still have some opportunity to say some more exotic cosmological source can also produce detectable gravitational background in the nanohertz range. For example, the cosmic string, domain wall, scalar-induced gravitational wave, and so on. But among all of these possible sources, I think the supermassive black hole binary provides the most promising candidate. So before closing my talk, another question we wonder is that we want to ask some fundamental question. The most important for us is that we know currently the general relativity is the best theory for gravity. But we know this general relativity is a classical theory. In fundamental physics, we also have another fundamental theory is quantum mechanics. And we know these two theories, the general relativity and quantum mechanics, is not comparable with each other. So once these two very successful theories are not compatible with each other, we have to at least modify one of them. Right? But we do not know whether we should modify gravity or modify the quantum mechanics. But now we try to use the new observation data to check whether we need to go beyond the general relativity or not. So before that, we need to clarify what's the fundamental prediction of general relativity for gravitational wave. So for us, we think there are three key predictions of general relativity for gravitational wave. One is the velocity of gravitational wave is the speed of light. Once we find the velocity of gravitational wave is different from the speed of light, we know we have to modify gravity. We have to modify general relativity. Another point is that the gravitational wave in general relativity is a quadrupolar radiation. And in general relativity, because there are diffeomorphism invariance, so general relativity predicts there are only two tensor polarization modes. If we observe more polarization modes, we can also definitely say that we need to modify general relativity. So, in order to check these three predictions, we can give us more mass for graviton. Once the graviton has a small mass, it will modify the correlation of TOA from different pulsars. And on the other hand, once the graviton has a mass, and there will be a cutoff in the frequency of gravitational wave, because once the graviton mass is not zero and the gravitational wave frequency has a lower bound. But now we detect a very low frequency gravitational wave. This will give us an upper limit on the mass of graviton, which is around 8.2 times 10 to minus 24 electronvolts. This is comparable to the constraint of gravitational mass from LIGO. But we didn't see any signal for a deviation from zero mass gravitational wave signal. So we can also introduce a simple dispersion relation. Here we introduce a parameter V here. If V equal 1, the gravitational wave, the velocity of gravitational wave is the same as speed of light. And for different parameter V, we can see that it will modify the overlap reduced function, the spatial correlation between the signal. And we use the NANOGrav 15-year dataset, and we find the lower bound for the gravitational wave, velocity of gravitational wave is 0.87. But anyway, the prediction of general relativity is still consistent with the current dataset. So another important thing for us is to check the polarization modes. As we say that the general relativity predicts that gravitational wave have two independent tensor polarization modes. Once we observe these four polarization modes, we can say that we have the gravitational wave must be the general relativity must be modified. And for most general metric, gravity theory can allow two vector modes, is longitudinal mode, and the two tensor modes. One is transverse mode, another one is longitudinal mode. Besides the two tensor modes in general relativity, and in pulsar timing array, we can measure the different polarization modes have different overlap reduced function. So this is general relativity predict the transverse traceless gravitational wave mode, and this is a famous Head-Stars curve. And for the scalar transverse mode, the spatial correlation is different, right? It's different. And here we have a three line here, and this is classified by the spin of this mode. This is tensor mode, this is scalar mode, and this is a vector mode. Actually, we can also have a different classification. For example, we have these three transverse modes and three longitudinal modes. And we find that for the transverse modes, we can have identified unified formula by introducing a parameter alpha here. So if alpha equals 3 is corresponding to the TT mode predicted by general relativity. If alpha equals 0 is corresponding to the scalar transverse mode beyond the general relativity. So it's interesting things that maybe 3 years ago in NANOGrav 12.5 years data. And we find strong evidence for the scalar transverse modes compared to the TT modes predicted by general relativity. It's much stronger than the TT modes predicted by general relativity. And we submit our paper in the early of 2021. And more than half years later, NANOGrav correlation tracked and reproduced our results. So here we roughly show the different prediction for the different polarization modes. So this is Helling-Stang's curve, and this is the scalar transverse mode. So because we find strong base evidence for this scalar transverse mode in NANOGrav 12.5 years dataset. So we also want to ask whether this signal still there or disappear in the new data, right? So it is interesting that we also do the data analysis. We find in NANOGrav 15 years dataset, we find the scalar transverse modes have a comparable base evidence compared to the TT modes. So we see that this signal is still there, and the best factor for the ST mode is still around 100. Is roughly the same as 12.5 years dataset is around 100. This is the best factor. So this one. Yes. It's around 100. Yes. But now, this two is comparable. It's 2 times different between ST and TT. No, ST is still have the best factor is still around 100. This best factor is comparable to TT. So TT is around 200. So this ST is still around 100, the best factor. And another possibility is that because now we have a large best factor for the TT modes and ST modes. So for us, we think there may be two polarization modes simultaneously in the dataset, right? So scalar transverse modes. This one, breathing modes. It is transverse to the propagation direction. Yes. So previously, I also introduced a new parameter alpha here, right? So we can simultaneously consider these two modes. So if alpha equals 0, it corresponds to scalar transverse mode, and alpha equals 3 corresponds to the TT mode. And it is very interesting that the NANOGrav 15 years dataset prefer alpha in the middle, not 0 and not 3. And a simple explanation is that this dataset include both of them. So here we consider, we take the ST and the TT modes into account simultaneously, and we find two peaks, right? So So if these data sets can be trusted, so it prefer there are both polarization modes. One is TT mode, another one is ST mode in their data set. So last year we also submit our paper maybe in on 17th October, and the next day NANOGrav also submit their paper, and fortunately our result is consistent with each other. So they also claim that their result is largely consistent with a similar study by us. So from the fundamental theory side, we know we need a quantum theory of gravity. But we do not know whether this scalar transverse modes can help us to build up a consistent quantum gravity theory of gravity or not. But anyway, for us, we know in almost all of the modified gravity theory, we have scalar modes. For example, FR theory and other modified gravity theory. So, but we still cannot connect such kind of scalar transverse mode to a really consistent quantum theory of gravity. But we hope we can find some connection between these two things in the future. Okay, that's all. Thank you very much.
Thank you. So it's very, very interesting. Can you go back to the vector case? Did you find any evidence for that?
No, we didn't find any vector. The best vector is quite small.
Right. And then when you combine them, the base factors don't change very much.
Yeah, and from the theory side, it's also very interesting. So usually, once we have longitudinal vector mode, this vector mode is longitudinal mode. And sometimes they will be ghost mode. It is not a good one for theory. And from the data analysis, we see that this longitudinal mode is not preferred by the data sets.
So can I see the Helling and Downs curve for these different?
Helling-Downs?
Yeah, this one.
Yeah, this is Helling-Downs curve.
So for a scalar, it's basically.
And this is the scalar transverse mode.
Right.
And this is the combination of these two modes. And give us the best fit to the data.
And you just fitted the Helling and Downs, that this data is the one you fit?
Oh, okay. We see that this data set is higher than the prediction of Helling-Downs curve, right?
But I'm saying, is this the only data set that you're fitting? Is this what you're showing here, or is there any other data?
You mean this violin?
Yeah.
This violin just data.
Okay.
Yes.
Because there is, I mean, the autocorrelation is also something, but you're not using.
This is cross correlation.
This is just cross correlation.
Yes. This is because the angular separation does not equal to 0. So this is
So one last thing, in terms of what systematics could be responsible for this. So this, if it's a scalar, it means that all the pulsars respond in the same way to this, right? So,
yes. This mode.
Yeah. So could that be like some sort of a clock, like the clock on Earth, if it's doing something weird?
No, the clock error generates monopole. This is not the scalar transverse mode.
I see. So this is different from
different monopole. This is different from the clock error. The clock error generates a monopole.
I see.
Yes.
Okay, thank you.
Thank you.
Yes, thank you for the talk. I have a question about the Helling-Downs curve. Behind the Helling-Downs curve, there are some assumptions, like the isotropical of the background and the evolution and so on. So actually, there are the real universe may also deviate from this assumption. It's called the cosmic variance.
Yes.
So in that case, we, how we are comparing our data with the Helling-Downs curve. So how do you?
So recently we have a new paper because I submitted my abstract several months ago. So I didn't talk this new topic in my talk. Yes, it's now I'm sure that the real correlation should not be the Helling-Downs curve. But I do not completely agree with the understanding of Bruce Island. They misunderstand the cosmic variance, like CMB. I think it's quite different. So even though there may be some uncertainty for us to calculate the spatial correlation, but in our universe, the phase is fixed because we only have one universe. We do not have such kind of variance, but we should have a correlation function different from Helling-Downs curve. So recently, we do many simulations, and we give from the simulation we work out the simple parameterization for this correlation function. And once we introduce some parameter, and we clearly see, we consider A frequency bins, and we see that all of these A frequency bins, the correlation different from Helling-Downs curve. And once we take this deviation into account, the evidence for gravitational wave background has been can be significantly enhanced. Yes, the optimal statistic SNR is enhanced to 6.6. Okay, please.
But according to my naive consideration, so it means that the Helling-Downs curve has some uncertainty, which it's I don't know. It's if you have many possibilities to realize a universe, the Helling-Downs curve has uncertainty.
Yes, but this Bruce Allen considered there should be many universe realization, right? But in our universe, we just have one universe.
But you don't know which one is this.
Yes, that's why we need to introduce some parameter.
Okay, extra parameter.
Yes, actual parameter. And like once we try to search for gravitational wave signal in LIGO, we hope we have a better waveform, right? Once we have a precise waveform, it will help us to enhance the signal to noise ratio, right? But for PTA, we do not, for this gravitational background in PTA, we do not talk about the waveform. We assume the energy spectrum has a power law spectrum. So key point is the spatial correlation, right? It's similar to the waveform for LIGO. So once we have a better waveform, which means the better means closer to the real case, right? We can enhance the signal to noise ratio. Okay, maybe we can talk later.
So this is interesting because I think I gave a talk about this 2 days ago in Qing-Guo, and we're discussing this question of optimal estimators for pulsar timing array. But basically, my understanding is that two-point correlation function is only optimal for Gaussian noise. But then pulsars are not pulsars. The supermassive black holes are discrete objects, so they have Poisson statistics, not Gaussian statistics. And that's why that this is suboptimal what they're doing. So on optimal one, you have to, you can do something better, including higher order correlations. But yeah, so I had a proposal for how to do it, but it's good that you've already done it. I guess the question is, what is really the best way? And again, we should definitely talk about this. Thank you.
Okay, thank you.
Okay, maybe I just have a little related or follow-up questions on this. So our interpretation for this Helling-Downs curve data in being the background, the gravitational wave,
Background.
stochastic background. But how do we know this is not from some like a far away cosmological distance, but a single source, which could also give us very similar signal? And in particular, you're showing that full data set is kind of being different from like a very recent data set results, right? So how can we rule out this is not some specific individual objects?
Oh, you mean the individual supermassive black hole binary?
Yes.
Yes. So for this low frequency gravitational wave signal for the for individual supermassive black hole binary, they will have the frequency is fixed, just around monochromatic. But here we find a spectrum. This signal exists in different frequency.
Sorry, I'm not talking about the polarization. I'm talking about earlier result.
Yes.
Right.
Okay.
In particular, you're saying the result only show up at a certain frequency.
No. For the NANOGrav, okay.
For the CPTA result, so that
Yes.
result is only shown up at one specific.
Yes, it's possible that I also suggest them to do such kind of analysis. They said that they will do, but they didn't publish any results to search for an individual supermassive black binary in their dataset. Actually, the NANOGrav and the EPTA, they also simultaneously consider the gravitational background and the individual supermassive black hole binaries. But they didn't find some significant base factor to support detection for the individual supermassive black hole binaries.
I see. Okay. Maybe another quick question is,
Okay,
you
please.
said you kind of extrapolate your estimation of that background to higher frequency.
Yes.
I just wonder, because the frequencies really go up to, I think it's this slide, go up to quite high frequencies. But here, what's the assumption going to there, your model?
Okay.
Is that still a supermassive binary black hole system?
Yes.
But I suppose they're
But
quite
have different mass. So that's why we say we extrapolate the low frequency background to the high frequency.
high frequency. I just wonder what's the astrophysical model actually goes to there.
Yes. We have to use this model.
Okay.
This model proposed by Chen, Cesana, and Consolis. If we have not this model, we cannot extrapolate it to high frequency region.
But what's roughly the supermassive black hole mass?
So here they consider the supermassive mass from 10 to 5 to 10 to 10 solar mass. And in the PTA frequency band, it's dominated by the maybe 10 to 9 to 10 to 10 solar mass supermassive black hole. But in the higher frequency, it's dominated by 10 to 5 to 10 to 8 solar mass. So the mass is different. But here we use this model, and they claim this model is applicable for the supermassive black hole from 10 to 5 to 10 to 10 solar mass. So we have to assume this model. Yes.
Thank you.
Okay, thank you very much.
Any more questions? Okay, if not, let's thank Qing-Guo's very wonderful talk. Thank you very much.
Thank you.